Hello, 30-1s. Here is the first lesson in our new unit, which is going to be all about exponential functions. What we're going to look at today is we're going to look at the graphs of these functions. Okay, well, maybe before we look at the graph of the function, let's think about why we're looking at exponential functions. Well, an exponential function is going to model a lot of things in nature. So some of the things that it's going to model certain types of populations. It's going to model investing money. It's going to model half-lives of substances. It models a ton of stuff. So this is how we carbon date dinosaur bones. This is how we can predict how much my money is going to be worth if I'm investing for a long time. It's going to help me predict what my population is growing or decreasing to. So this is some serious applications here. Now, before we get into those applications, let's look at the graph of these things. What I would like you to do here is we're going to look at the graph of 2 to the exponent x and 1/2 to the exponent x. If you need to, pick up your graphing calculator. I want you to fill in the table of values. I want you to draw me your graph, and I want you to complete the table below. So hit pause and try all of that. Okay, I'm hoping that you paused it and found all these values yourself. If you had to use your graphing calculator, all I did was I just subbed in my x values into each of my functions. Okay, let's go graph this. Well, look at what happens here. I get -3 is 1/8. Well, that's hard to draw. It's somewhere really close to that x-axis, isn't it? -2 is 1/4. Well, it's a little bit higher up, but it's still difficult for me to draw. And 1/2, and then 1, and then 2, and then I skip over to 8. I mean, I could have done 2 is 4, but for some reason when I typed this, I skipped x was 2 because I'm crazy. Okay, what does this graph look like? It does this. This graph is the graph of y is equal to 2 to the exponent x. This graph never hits the x-axis. The more negative our x values get, the closer to 0 we will approach. We're starting to talk a little bit about calculus here. As x goes to -infinity, the y values approach 0. Okay, I'm going to draw the other one, 1/2 to the x. Well, what I'm wondering is, did you notice that these are mirrors of each other? They are horizontal reflections, just like that. And I should just fix up that bottom there. So again, what's going to happen as the y values go to positive infinity, as the x values go to positive infinity, the y values are going to approach 0. They will never touch the x-axis. So what's happening here is there is an asymptote, just like that. Just like that. There's an asymptote at y equals 0. Okay, how would I describe these graphs? They're both exponentials. Well, this first graph here, I would call it increasing. The second graph here, well, then you're guessing it's going to be called decreasing. Well, I could also call the first graph a growth, and I could call the second graph a decay. I could say appreciating and depreciating. So it's going to depend on the context of the question, but those are your kind of general ways to describe these graphs. Well, what's my domain and range for these things? Where it says y is equal to b to the exponent x. So we just grew 2 to the exponent x and 1/2 to the exponent x, where b can't be 1. All right, we'll talk about why b can't be 1 in just a second. Well, your domain will be infinite. Never stops going. The x values go to -infinity. They go to positive infinity. The range is greater than or equal to 0. I lied. It's just greater than 0. Why did I say one thing and write something different? It's greater than 0. Okay, x-intercept. You don't have one unless we transform this graph, which is the next lesson. I really need you to know that your initial y-intercept is at 0, 1. That's going to be really important coming up. And the equation of your asymptote is y is equal to 0. Also, incredibly important when we start transforming these graphs in the next lesson. Okay, why can't b equal 1? Well, if we let this base be 1, 1 to the exponent of anything is 1. We wouldn't have an exponential. We would have a horizontal line. So what values can b be? The values for b that we're going to have, if we're increasing, our base is going to be bigger than 1. And if we're decreasing, our base will be smaller than 1, but bigger than 0. Okay, that's the important part of increasing and decreasing. I can tell by looking at the base if I'm going to be increasing or decreasing. Base is bigger than 1, increasing. Base is smaller than 1, but bigger than 0, decreasing. Okay, there's your basics. You should memorize those two things. Now, what about if we tried to graph this in our calculator? Well, I've got 2 to the exponent x plotted in here. What's going to happen when we draw this? Let's see. So I'm going to hit graph. There's our graph. But the thing about our graphing calculator here is it's not doing a very good job. If you were looking at that graph for the first time, you would maybe say this graph looks like it touches the x-axis. It certainly doesn't. So our graphing calculators aren't doing a great job here, are they? Whereas if we look at a better graphing program, this is called GeoGebra. You might start learning how to use it in university. As we zoom in, what we can see is there's our decreasing graph, there's our increasing graph, is that these graphs never touch the x-axis. Even if we zoom in as close as we want, every time I zoom in, it's never going to be touching the x-axis unless we start to transform these like we will in the next lesson. Now, the last thing we want to look at here is, again, the purpose of this is to look at the applications of this. A normal application is talking about population curves. So we'll talk about people here. We'll get a lot of questions about bacteria. So the question says there's a population of 5,000 people is growing at a rate of 2% annually. We're going to write the function for this. Now, when we're writing these, it's going to be expressed in this form, ABT over P. Well, in your first lesson, in your first set of homework, I should say, this will be made for you. But I want you to know where it comes from before you look at those questions. A, well, we know A is our vertical stretch, but in terms of a contextual question, this is the initial amount. So it's how many people I start with. B is our rate of growth. T is time that has passed. And P, well, that's our period. It's the time it takes to repeat. So in your homework, this will be made for you. But where does this equation come from? Well, the initial amount, A, I have 5,000 people. I'm going to skip the B value for a second. T is time. Well, I'm making an equation. Time can change. So T is T. Period. Well, annually, Well, 1. So when you're doing questions in your homework, you'll maybe see different values there. We'll talk about that as we get to them. Okay, what about our base? This is the big question. Well, what I want you to think is at time 0, when I hit my stopwatch and I start, what percentage of the population do I have? Well, I have 100% at time 0. And what this question tells us, or the statement, says it grows at 2% annually. So a year later, what percentage of the population do I have? Well, I have 102% because I grew by 2%. I'm going to write this a bit strange. This is 100 plus 2, right? That's where we got that from. Okay, this is how we're going to write our base. We're always going to think of our base as starting at 100. If we're increasing, we're going to add to it. If we're decreasing, we're going to subtract. I start with 100%. Where am I at the end of the year? And then all we're going to do is this. We're going to turn that percentage into a decimal. 102% is 1.02. So when you're going through your homework, that's where that function comes from. This value is how many I'm starting with. This is my rate of change. This is my period. Okay, let's try just one more. What if I said we had this? I'm going to say a population of a town is currently, I don't know, 30,000 and is decreasing by 10% annually. What would this function look like? Well, this will be a b to the t over p. I think everyone sees that the a value is 30,000 when they do these questions for the first time. T over 1, the periods annually, where a lot of people struggle is coming up with the base. I'll see this a lot for the base, 0.10, which is really wrong. Think of it again like this. I start with 100%. What happens? At the end of the year, I lose 10%. What remains? 90%. What's that as a decimal? 0.90. There's your function. There it is. In your homework, you'll be asked to solve these things graphically, which again, you're really good at this point. You're just subbing them into your calculator. There it is, friends. There's your first lesson in exponentials.